Hi everyone. For this video we will compute the fictitious forces, also known as inertial forces, that arise in a rotating frame of reference. We go on to use this knowledge to compute the motion of a Foucault pendulum. We describe the Eötvös effect, the deviation we expect from a sniper shot, and how these forces affect weather systems. First thing we should do is discuss rotations. Supposing in 2 dimensions we have a rotation. So basis vector E1 gets mapped to E1 primed. E1 primed is going to be cos theta sine theta, and E2 gets mapped to E2 primed. E2 primed minus sine theta cos theta. Now we want to consider what happens in 3 dimensions, so we have a third basis vector, E3 maps to E3 primed, which is out of the screen. Therefore, we can write down the matrix of the rotation with respect to this basis. And we find R is equal to, well, the first column is the image of the first basis vector. So we'll get cos theta sine theta, and we should add a 0 for the third component if we extend the basis to 3 dimensions. The second column is minus sine theta cos theta 0. And finally, the third column is 0, 0, 1. And what we can notice is that the transpose is the rotation, but with the angle minus theta. Rotation with angle minus theta is just the inverse map. So we know that R transpose R and R transpose are equal to the identity. Note also the determinant R is equal to 1. Now these conditions in 3 dimensions characterize a rotation. To see this, suppose R transpose is the identity and the determinant of R is 1. Then first look at the determinant of R minus I. Well, I can multiply that by the determinant of R transpose, which is 1, and that gives me the determinant of R transpose R minus R transpose, which is the determinant of I minus R transpose. This is equal to the determinant I minus R, and it's also up to minus 1 cubed, the determinant of R minus I. In other words, it's minus the determinant of R minus I. So det of R minus I is equal to 0. Therefore, there exists a non-zero vector n such that Rn is equal to n, and that's going to be our axis. Notice that Rx dotted with Ry is equal to x transpose R transpose Ry is x transpose y is x dot y. So rotations preserve dot products. We will assume that n is normalized, and we take L and n to be unit vectors in the plane orthogonal to n. Then RL is orthogonal to n because n is Rn, and RL has unit length. Therefore, RL can be written as cos theta L plus sine theta m, because L and m span the space orthogonal to n. Similarly, Rm must be both orthogonal to n and orthogonal to RL. So therefore, it must be equal to either plus or minus sine theta L plus cos theta m. Therefore, we can write down the matrix for R with respect to the basis LMN. There are 2 possibilities. Now we also require determinant of R to be equal to plus 1. So that means we must have the upper signs. So we get cos theta sine theta 0 minus sine theta cos theta 0, 0, 0, 1, which is the rotation matrix we had earlier. Next, suppose that x at time t is a rotation applied to x naught. Then x dot of t is r dot x naught, which is r dot r inverse of x, and that's r dot times r transpose of x. Let A be r dot r transpose. Now, r transpose is the identity, so taking the time derivative of this gives me r dot R transpose plus R transpose dot is 0. Or in other words, A plus A transpose is 0. So A is antisymmetric. Now any 3 by 3 antisymmetric matrix can be written as A equals 0 minus omega 3, omega 2, omega 3, 0 minus omega 1, minus omega 2, omega 1, 0. And then AX would be equal to minus omega 3 y plus omega 2 z, omega 3x minus omega 1 z, minus omega 2x plus omega 1 y, which is omega cross x, where omega is omega 1, omega 2, omega 3, is the angular velocity vector. Next, suppose we have basis EI, which depends on time. EI of t is rotating. So EI of t is the rotation times EI at time 0. Then EI dot is equal to omega cross EI. Let x, t, be a vector, which we expand in terms of the basis EI. Here I'm using the summation convention, so we sum over I because it's repeated. X dot is then xi dot EI plus xi EI dot. That's xi dot EI plus xi omega cross EI. That's xi dot EI plus omega cross x. Now let us assume that the original frame is inertial. Then we have x dot in the inertial frame is equal to, well, this term here is xi dot as measured in the rotating frame. And that is because in the rotating frame we do not see any motion of the basis. Now what I've labelled as inertial, we don't actually require it to be inertial at this stage. I'll point out later when the assumption that it is an inertial frame becomes important. So when differentiating vectors, we have that the time derivative in the inertial frame is the time derivative in the rotating frame plus the cross product with omega. In particular then, d by dt of x inertial dot in the inertial frame, which is x double dot in the inertial frame, is d by dt in the rotating frame of x dot in plus omega cross x dot in. That's d by dt in the rotating frame applied to dx by dt. That's d by dt in the rotating frame of dx by dt in the rotating frame plus omega cross x plus omega cross dx by dt in the rotating frame plus omega cross x. And that's equal to d2x by dt in the rotating frame plus omega cross dx by dt in the rotating frame times 2 plus d omega by dt in the rotating frame cross x plus omega cross x. In other words, the acceleration in the inertial frame is the acceleration as measured in the rotating frame plus twice omega cross the velocity in the rotating frame plus omega dot cross x plus omega cross x. Or rearranging, the acceleration in the rotating frame is the acceleration in the inertial frame minus omega dot cross x minus 2 omega cross v in the rotating frame minus omega cross x. The first term is the Euler acceleration. The second term is the Coriolis acceleration. And the final term is the centrifugal acceleration. So far, we have not used the fact that we were working initially in an inertial frame. This shows that the derivation of the Coriolis and centrifugal, and indeed the Euler accelerations, are purely mathematical transformations. We have not used any physics whatsoever. So the Coriolis acceleration, centrifugal acceleration, and Euler acceleration will occur independent of the laws of physics. So it is incorrect to argue that the Coriolis acceleration, for instance, is a result of conservation of momentum. Now, if we do assume that the initial frame was an inertial one, then we can write this as F over m minus omega dot x dot minus 2 omega cross v rot minus omega cross x. So that's for an inertial frame, where Newton's second law holds. So what we have shown is we can use Newton's laws, provided in addition to the forces we have in the inertial frame, we include the Euler acceleration, Coriolis acceleration, and centrifugal acceleration. Let's look at an example. Consider the fixed stars. In the inertial frame, we have x dot equal to 0. So that's x dot in the rotating frame plus omega cross x. So therefore, the velocity in the rotating frame is minus omega cross x. And therefore, the Coriolis acceleration is minus 2 omega cross minus omega cross x is 2 omega cross x. And the centrifugal acceleration is minus omega cross x. So the total acceleration is just omega cross x, which is omega dot x times omega minus omega squared x, and that's a centripetal acceleration. And here we're assuming that we're looking at the rotation of the Earth, so that omega is 2 pi radians per day, strictly speaking per sidereal day. So the motion of the fixed stars obeys the equation x double dot is equal to omega cross x. Take omega equal to 0, 0, scalar omega. That's just choosing a basis. So in component form, we have x double dot, y double dot, z double dot is equal to minus omega squared x, y, 0. And x dot at time 0 is minus omega cross x at time 0 is minus 0, 0, 1 crossed with x 0, y 0, z 0, omega y 0 minus omega x 0, 0. In particular, z double dot is 0, z dot is 0 at time 0, and z at time 0 is z naught. And that implies z is z naught for all time. Let zeta be x plus iy. Then x double dot equals minus omega squared x, and y double dot equals minus omega squared y, imply that zeta double dot is minus omega squared zeta. And zeta dot at 0 is minus I omega zeta at 0. We can solve this. Zeta is equal to a e to the minus I omega t plus b e to the I omega t. And then zeta dot at time 0 is minus I omega a minus b, and that's got to be to minus I omega a plus b. So b is equal to 0, and therefore zeta is a e to the minus I omega t. Let a be r e to the I phi, and the real part tells me that x is equal to r cos omega t plus phi, and y is minus r sine omega t plus phi. And we still have z is equal to z naught. Now this solution is with respect to coordinates centered at the center of the Earth. If we are not at the center of the Earth, if we are located at position A, which is A0, B0, C0, then with respect to bases centered at that point, let's call that capital X, little x minus A. So x is minus A0 plus r cos omega t plus phi. Y is minus B0 minus r sine omega t plus phi. And z is minus C0 plus Z0. So this represents circular motion about a point slightly offset from the center. If we're looking at the stars or the sun, r is considerably greater than the magnitude of the vector a, and so essentially the fixed stars appear to rotate about us. Notice that if this is the Earth rotating in this direction, so that's the North Pole, and we have a star up here and another one, say, down here, then as seen from the Earth, our equations tell us that the rotation is in the opposite direction to the rotation of the axes. So we observe clockwise star trails in the southern hemisphere and anti-clockwise star rotation in the northern hemisphere. That result was not surprising, but it emphasized that we need to apply the centrifugal and Coriolis accelerations to the stars themselves in order to get the correct motion in our rotating frame. Now let's examine the Foucault pendulum. We have the Earth. Let us consider a point on the Earth and construct a basis which is vertically upwards. We call that EZ. We'll have E north, and we'll have a third vector into the screen, which would be the easterly So E east, E north, EZ is a right-handed orthonormal basis. Let lambda be the latitude. So that angle is also lambda. Then omega is scalar omega times 0 for the easterly component. The northerly component is going to be cos lambda, and the vertical direction is going to be sine lambda. Again, scalar omega is 2 pi per day. We can neglect the centrifugal acceleration because we can incorporate it into a local change in the gravitational acceleration. We consider a pendulum where the length is very long, so we assume we have simple harmonic motion. X is x, y, z, and this is x, e east, plus y, e north, plus z, e z. And these equations hold if there's no rotation. What are the equations if we include the effect of the rotation of the Earth? The acceleration is minus twice omega, naught cos lambda sine lambda, crossed with x dot y dot z dot, minus omega squared x y z, plus 0, 0, f. Where f is an acceleration which we're not really interested in, it corresponds to what it takes to make z double dot equal to 0, or approximately equal to 0 in this case. So x double dot y double dot z double dot is minus 2 omega times minus sine lambda y dot, sine lambda x dot. Let's not worry about the z component, minus omega squared xy. Let zeta be x psi y. Then we have zeta double dot plus 2i omega sine lambda zeta dot plus omega squared zeta is 0, combining the two components. Well, we can solve that. Zeta is equal to r e to the minus I omega sine lambda t plus I phi cos omega primed t minus t naught, where omega primed is the square root of omega squared plus little omega squared sine squared lambda. And we look for a solution. If we neglect the Coriolis term, we have motion in a plane. Taking the real and imaginary parts gives me x is r cos omega sine lambda t plus phi cos omega prime t minus t naught, and y is minus r sine omega sine lambda t plus phi cos omega prime t minus t naught. So therefore y over x is minus tan omega sine lambda t plus phi, and now write x is r cos theta, y as r sine theta, and that shows that theta dot is minus omega sine lambda. So theta is the plane of rotation, and theta dot in the northern hemisphere will be negative. So that shows a Foucault pendulum rotates clockwise in the northern hemisphere at a rate of omega sine lambda. In the southern hemisphere, it rotates anti-clockwise at the same rate. For our next example, we discuss the Eötvös effect. We have x double dot is minus 2 omega cross x dot minus g ez, again neglecting the centrifugal force. X dot will take to be ve vn 0, so we assume the horizontal velocity is a lot larger than the vertical component of the velocity. X double dot is minus 2 omega naught cos lambda sine lambda cross ve vn 0 plus naught naught g. Let's write that as a minus g. Minus 2 omega times minus vn sine lambda ve sine lambda minus ve cos lambda minus naught naught g. In particular, the z double dot is 2 omega ve cos lambda minus g, which is minus g effective. So if we're in a plane flying in the easterly direction, we have ve greater than 0, and the effective gravitational acceleration reduces. In the westerly direction, ve is negative, and the effective gravitational acceleration increases. And that's relative to flying, say, north or the south direction, or not moving at all. This is the Eötvös effect. Let's consider a marksman aiming at a target. What is the effect on the Coriolis force on the path of the bullet? The equations are x double dot y double dot is 2 omega En sine lambda minus 2 omega Ve sine lambda. So these are the same equations that we had earlier on. That's 2 omega sine lambda Vn minus Ve. If the velocity is Ve Vn, then this shows the acceleration is orthogonal to it, and in the northern hemisphere it points to the right. And so the bullet will deviate to the right, fired in a different direction. The acceleration is still to the right. In the southern hemisphere, the deviation will be to the left. Well, let's work out the deviation. Delta is going to be a half at squared, where a is twice the magnitude of omega sine lambda. So this is the deviation we would expect after time t from the firing of the bullet. We assume the target is a distance d equal to vt away, so delta is equal to omega sine lambda mod vt squared er, where er is a unit vector orthogonal to the initial direction of travel of the bullet. Over the path of the bullet, we assume that v remains effectively constant. And that's omega times dt sine lambda er. And you'll notice that it's independent of the direction you fire the bullet, whether that's north, east, southwest, or any other direction. Now, what about the vertical displacement? In the equations that I wrote down here, I didn't write down the z double dot expression. Well, that's because essentially it comes from the same formula we use for the Eötvös effect. So the displacement in the vertical direction is a half times 2 omega Ve cos lambda t squared, which is omega Ve cos lambda t squared. So if Ve is greater than 0, so for instance if we fire in the easterly direction, we end up hitting above where we aimed compared to firing, say, in the north or southerly directions. And if we fire in the westerly direction, we hit below the target as compared to firing in the north or south directions. Finally, let's try and understand what happens to weather systems. If there's the Earth and we have a low pressure system in the northern hemisphere, then air rushes in towards the low pressure but is always directed to the right. That causes a circulation anti-clockwise. Hurricanes rotate anti-clockwise in the northern hemispheres, and cyclones rotate clockwise in the southern hemisphere. And that completes our delve into the mathematics and physics of fictitious forces.